The cancellation properties of inverse trigonometric functions. Hello everyone. Today, we are going to explore the cancellation properties of inverse trigonometric functions. To begin, let's establish a fundamental concept. In mathematics, an inverse function is essentially designed to undo the action of the original function. When we compose a function with its inverse, meaning we apply one immediately after the other, they effectively cancel each other out, which returns us to our original input value. In the specific context of inverse trigonometric functions, this mathematical relationship is known as the cancellation property. However, there is a catch. Because trigonometric functions are periodic, meaning they repeat their values at regular intervals, these cancellation properties are not universal. They do not apply to every possible value. Instead, these properties are strictly governed by two critical factors: the domain of the inverse function and the principal value branch of the trigonometric function. As we move through the next few slides, we will examine exactly how these restrictions work and how to apply them to avoid common mistakes. 1. The first type of cancellation, f(1x) equals x'. Now, let's dive into the first type of cancellation. This specific scenario occurs when the inverse trigonometric function is the inner function and the standard trigonometric function is the outer function. Let's look at the sine function as our primary example. The identity here is expressed as the sine of the inverse sine of x equals x. However, we must be careful about when this is actually true. This property is valid only if x falls within the domain of the inverse sine function. Since the domain of the inverse sine of x is the interval from -1 to +1, this property holds true if and only if x is between -1 and 1, inclusive. To help you visualize this, let's follow the logic step by step. First, suppose we start with a value x that is between -1 and 1. The inner part of the expression, the inverse sine of x, is essentially asking, what angle, which we can call theta, has a sine value equal to x? Then, when we apply the outer sine function to that angle theta, we are asking, what is the sine of the angle whose sine is x? Naturally, the two operations cancel each other out, and we return to our original value, x. This same logic extends to other trigonometric functions, provided that x stays within their respective domains. For instance, the cosine of the inverse cosine of x equals x, as long as x is between -1 and 1. Similarly, the tangent of the inverse tangent of x equals x in the case of tangent. This property is even broader, as it holds true for all real numbers. While this first type of cancellation is relatively straightforward, keep in mind that the order of functions matters. In the next slide, we will examine what happens when the trigonometric function is on the inside and the inverse is on the outside, which requires a bit more caution. To the second type of cancellation, f(1fx) equals x'. Now that we have explored the first type of cancellation, where the inverse function was on the inside, let us move on to the second type of cancellation. In this scenario, the roles are reversed. This property occurs when the trigonometric function acts as the inner function and the inverse trigonometric function is the outer function. Let us examine the case of sine. The identity is expressed as inverse sine of sine x equals x. However, it is crucial to note the condition for validity. Unlike the first property we discussed in the previous slide, this identity is not universally true for all values of x. It is valid only if x lies within the principal value branch of the sine function. For the inverse sine function, the principal value branch is the interval from -π/2 to π/2. Therefore, this property holds true if and only if x is between -π/2 and π/2. To help you understand why this restriction exists, let us walk through the step-by-step logic. First, we start with an angle, x. When we apply the sine function to x, we are calculating the ratio associated with that angle. Then, the inverse sine function takes that ratio and looks for the angle, specifically within the principal range, that produces that same ratio. If the original angle x was already within the principal range, the result is simply x, and the functions effectively cancel each other out. However, if x is outside this range, the inverse sine function will not return the original angle. Instead, it will return a different angle that is related to x via trigonometric identities, but strictly falls within the range of -π/2 to π/2. This same principle extends to other trigonometric functions. For cosine, inverse cosine of cosine x equals x, provided that x is within the interval from 0 to π. Similarly, for tangent, inverse tangent of tangent x equals x, as long as x is between -π/2 and π/2. To make these concepts more intuitive, in the next slide, we will use a lock and key analogy to better understand these restrictions. 3. Conceptual analogy, the lock and key. Now, to help you visualize the two types of cancellation we have just discussed, let us use a real-world analogy. Imagine the trigonometric function as a lock and the inverse function as the key designed to open it. In a simple scenario, when you use the key to open the lock, you return to the original state. This represents the basic idea of an inverse function undoing the action of the original function. However, in trigonometry, the lock is a bit unusual. Because trigonometric functions are periodic, meaning they repeat their values at regular intervals, this lock can actually be opened by many different keys or different angles that all produce the same output. This is precisely why we need the principal value branch. You can think of this branch as a strict rule that says, even if many different keys could technically open the lock, we will only ever recognize and use one specific key from a designated keychain. Keeping this analogy in mind will be very helpful as we move into the next slide, where we will apply these concepts to some worked examples. 4. Worked examples. Now that we have discussed the theoretical framework and the lock-in key analogy, let us apply these concepts to some practical problems. Please look at slide 5, where we will walk through two different types of examples. Let us begin with example 1, which illustrates a simple cancellation. We are asked to evaluate the sign of the inverse sine of 0.5. First, we identify the inner function, which in this case is the inverse sine of 0.5. Next, as we discussed in our second slide, we must verify the domain. We check if the value 0.5 falls within the required interval of -1 to 1. Since it does, the cancellation property is valid. Because the condition is met, we can directly apply the property where the sign of the inverse sine of x equals x. Therefore, the result is simply 0.5. Now, let us move to example 2, which is more nuanced because it involves a range restriction. Here, we are asked to evaluate the inverse sine of the sine of 2π/3. Following the same process, we first identify the inner function, which is the sine of 2π/3. Now, we must check the principal value branch, a concept we detailed in slide 3. The angle 2π/3 is approximately 120 degrees. However, the principal range for the inverse sine function is strictly between -π/2 and π/2, which corresponds to -90 to 90 degrees. Since 2π/3 lies outside this principal range, we cannot simply cancel the functions. If we did, we would arrive at the wrong answer. Instead, we must first calculate the actual value of the inner function. The sine of 2π/3 is equal to the square root of 3/2. Now, we evaluate the outer function using this value, the inverse sine of the square root of 3/2. Our goal here is to find the angle that falls within the principal range of -π/2 to π/2, whose sine is the square root of 3/2. That specific angle is π/3. Thus, the final result for this expression is π/3. Please take note of the difference between these two examples. In the first, the functions canceled out perfectly, but in the second, the range restriction forced us to perform extra steps. This leads us directly into our next slide, where we will discuss the most common mistakes students make when handling these properties. 5 common mistakes. Now that we have walked through the theory and some worked examples, let's discuss some common pitfalls to avoid so you don't lose marks on these types of problems. First, let's address the issue of ignoring the domain. A frequent mistake is assuming that the sign of the inverse sign of x always equals x, regardless of the value of x. For instance, if you encounter the expression sign of inverse sign of 2, you might be tempted to simply cancel the functions and say the answer is 2. However, this expression is actually undefined. This is because the inverse sign of 2 does not exist, as the sign of any angle must always fall between -1 and 1. Next, we have what I call blind cancellation. This occurs with the second type of property we studied. The most common error here is assuming that the inverse sign of the sign of x always equals x, no matter what the angle is. As we saw in our previous example with 2π/3, you cannot simply cancel the functions if the angle is outside the principal value branch. Always check if your angle falls within that specific range before you proceed with cancellation. Finally, be careful not to confuse these two different properties. To keep them straight in your mind, remember that the first case, where the inverse function is the inner function, is generally simpler, as it only requires the value to be within the valid domain. The second case, where the trigonometric function is the inner function, is more complex because it requires the angle to be within the principal range. Keeping these distinctions clear will be very helpful as we move into our final slide, where we will summarize all these conditions in a key takeaways table. 6 key takeaways. To wrap up our lesson, let's look at this summary table, which consolidates everything we have discussed regarding the cancellation properties of inverse trigonometric functions. First, let's examine the top 3 rows, where the trigonometric function is the outer function. As we noted in our earlier slides, these cases are generally more straightforward because we only need to ensure that the input is within the valid domain of the inner inverse function. For the first entry, the sign of the inverse sign of x equals x, provided that x is between -1 and 1, inclusive. Similarly, the cosine of the inverse cosine of x equals x, also as long as x is between -1 and 1, inclusive. For the tangent function, the tangent of the inverse tangent of x equals x for all real numbers, since the domain of the inverse tangent function is unrestricted. Now, let's move to the bottom 3 rows, where the inverse function is the outer function. Please recall our lock and key analogy and the warning against blind cancellation from the previous slide. In these cases, the result is only x if the angle falls within the specific principal value branch. First, the inverse sign of the sign of x equals x, but only if x is between -π/2 and π/2, inclusive. Next, the inverse cosine of the cosine of x equals x, provided that x is between 0 and π, inclusive. And finally, the inverse tangent of the tangent of x equals x, as long as x is strictly between -π/2 and π/2. I encourage you to keep this table as a reference. By always checking these constraints before canceling, you will avoid the common mistakes we discussed and ensure your calculations are mathematically sound.